In this video, we'll discuss about context-free grammar. So what is the definition of the context-free grammar? First, it is defined using a 4-tuple notation. G is equal to VTPS, where V is representing the variables or non-terminals, and T is representing the terminal symbols, and P is representing the production of the form capital A to alpha. Clearly, capital A is denoting a non-terminal capital V, and alpha is taken as a combination of terminals and non-terminals, V union T. Okay. And finally, capital S will be representing the start symbol. Okay. And here we represent both terminals and non-terminals as a finite set of symbols. Okay. And consider an example for the context-free grammar. Okay. Again, the representation is G is equal to VTPS. And what is the non-terminal in this particular grammar? Okay. Productions are basically representing the grammar. And in this grammar, you can see capital S is the non-terminal symbol. And the terminal symbols are small a and small b. Okay. So, non-terminal is capital S. Isn't it? Now, let us generate a sequence of strings that are possible or derivable from this particular grammar. Okay. So, starting from the shortest length string, first capital S tends to epsilon. It means we can generate epsilon from capital S. So, in the language, epsilon is generatable. And then consider capital S tends to small a capital S, small b capital S. Now we can substitute capital S as epsilon. So this is a epsilon, b epsilon. Okay. So it will become ab. So the string is ab here. Okay. And similarly, now consider capital S tends to small b capital S, small a capital S. And here we can substitute capital S as epsilon. So b epsilon, a epsilon, it will be ba. Okay. Like this. And similarly, we can generate another string here from bs, as. First, I will substitute s as epsilon. And the second S is substituted as BS, AS again. Okay. So, where you can generate BA, B, S is epsilon. And again, the second S is also epsilon. So, you will get a string like BA, BA. Okay. BA, BA. Let us suppose in this S, if I simply substitute AS, BS and substitute capital S as epsilon, in that case you will be able to generate a string like BAAB. And similarly, when you start capital S as AS, BS and capital S can be replaced with again AS, BS, where capital S is replaced with epsilon. In such case, you will generate a string like ABAB. And also you can generate string like ABBA and so on like this. So if you consider all these strings which are generatable from this grammar, in every string the number of A's and number of B's are equal. Okay. It means this grammar is going to generate a language containing equal number of A's and equal number of B's. And clearly the order of A's and order of B's doesn't have any restriction. A's can appear before B's and also after B's. So it means it is clearly generating set of all possible strings over the terminals A, B containing strings with equal number of A's and equal number of B's. So this is how we can generate the language from the given grammar. Now consider another context free grammar. Again, the notation is G is equal to VTPS. So what is V here? Which is a non-terminal. So the non-terminal that is represented in this productions is capital S. And what are the terminal symbols in these productions? Left parenthesis and right parenthesis are the terminal symbols. Okay. And what is a start symbol? Start symbol is capital S. Okay. So now we will consider generating the strings from these productions clearly. So capital S can generate epsilon. So you can see set of symbols. Okay. You can see clearly the language generated by this particular grammar contains epsilon. And next, capital S tends to left parenthesis, capital S right parenthesis. Now I'll replace this capital S with epsilon. It will become left parenthesis, epsilon, right parenthesis. Now you can write it as left parenthesis and right parenthesis. Okay. And similarly, I'll consider capital S as left parenthesis, S right parenthesis. Now this capital S can be replaced as again left parenthesis, S right parenthesis. Now you can replace this capital S as epsilon, left parenthesis, right parenthesis, right parenthesis. So you will be able to generate a string like left parenthesis, right parenthesis, right parenthesis. Okay. And now I'll consider another production like capital S tends to capital S, capital S. Here, first I will substitute capital S as left parenthesis, S right parenthesis, and another S as left parenthesis, S right parenthesis. Now S can be replaced with epsilon. So this is epsilon, and here also epsilon. Now you can write it as left parenthesis, right parenthesis, left parenthesis, right parenthesis. Okay. So another string is clearly left parenthesis, right parenthesis, left parenthesis, right parenthesis, and so on like this. So what type of strings that can be generated from this context-free grammar? Okay, clearly there is a balanced parenthesis in every string that is generated from this grammar. Okay, even epsilon is possible when the number of left parentheses and number of right parentheses are 0, and here you can see there is one left parenthesis and one right parenthesis. Here there are two left parentheses and two right parentheses. Okay, like this. Number of left parentheses are equal to number of right parentheses, which means there is a balanced parenthesis. Okay, the list of strings generated by this grammar will have balanced parentheses. And this is very much useful in programming languages and compilers because when you write a program, automatically the program contains parentheses. You can see this type of parentheses you will observe in function calling or function implementation clearly. Parameters are parsed, okay, within a parenthesis which looks like this. It can be actual parameters or formal parameters, right? So in the program there should be equal number of left parentheses and equal number of right parentheses. Okay, so that can be checked with the help of the context-free grammar similar to this one. Okay. Now consider this gate question and check which is the correct option. Okay. So this is the given language. Okay. So this is a given grammar basically, and you need to identify the language that is generated by this grammar over alphabet A, B. Okay. So first identify the list of strings which can be generated from this grammar, and then we will be able to identify the language from the pattern that can be observed by the list of strings generated from this grammar. Okay. So I'll consider first taking the smallest string generated from this grammar. So capital S tends to small a. Okay. So language L is equal to clearly small a, and then capital S tends to small b. So small b is also generatable from this grammar, and capital S tends to small a, capital S small a. So you can see here capital S can be replaced with small b, where you can write ABA, ABA. Okay, and similarly capital S can be replaced with small a also. So you will be able to generate a string like triple A. Okay, and consider another possibility. S can be replaced with BSB, where we can substitute capital S as a small a. So this will be BAB. So BAB is another string that can be generated. And similarly, capital S tends to BSB, and now this S can be replaced with B. So this will be BBB, and so on like this. So these are the list of strings that can be generated from the grammar. Okay. So if you look at these strings clearly, the property that you can observe here is all these strings are palindrome strings, and the length of these strings is odd. Okay, you can see length of this and this string is 1, which is odd, and length of these 4 strings are odd, as the length is 3. Okay, so palindrome because if you reverse this string also you will get the same string. ABA, reverse of ABA is again ABA, and triple A, if you reverse also you will get the same string. BAB, reverse of this is again BAB. Triple B, reverse of triple B is triple B itself. So all the strings that are generatable from this grammar is clearly odd length palindromes. So the correct option is B. Okay. So next one is again the grammar is given and you need to identify the language generated by this particular grammar. Okay. So let us generate small strings that are possible from this grammar. So I'll consider capital S as capital X, capital Y, and now I will replace this capital X with a small a, and capital Y I'll replace with epsilon. So you will be able to generate a string like small a. Okay. Now consider another one. Capital S tends to capital X, capital Y. Okay. So here in capital X I will substitute small a, capital X. Okay. And capital Y can be replaced with epsilon, and this capital X can be replaced with a small a. It will be a. Okay. Now similarly capital S tends to capital X, capital Y. Here we can again substitute capital X as small a, and capital Y can be replaced with small a, capital Y, small b, and here I can substitute capital Y as epsilon. So it will become AAB. Okay. And consider another string, capital S tends to, so capital X, capital Y. This time we can substitute capital X as a small a, capital X, and capital Y can be substituted as small a, capital Y, small b. And you can replace capital X with small a, and capital Y can be replaced with epsilon. You will get triple A and then B. So like this, you can generate strings like this, which is small a, double A, double AB, triple AB, and so on like this. So from this, what you can observe is clearly, okay, from these languages, okay, from these strings which are part of this language, you can understand clearly the number of b's can be 0. Okay, if you observe strings like this and like this, there are no b's at all. Okay, it means when you try to represent this language of the form small a power m, small b power n, here the number of b's can be 0. Okay, so clearly n can be greater than or equal to 0. And how about number of m's? So number of m's, which means basically number of a's are represented by m. Okay, so what is the value of m here? Is m greater than n or equal to n? Okay, it is strictly greater than n. Why? Because you don't see any string with equal number of a's and equal number of b's at all. Okay, always the number of a's that are generated is greater than the number of b's. So m value should be strictly greater than n. So this is the language, isn't it? Okay, so we can generate a power m, b power n such that m is greater than n and n is greater than or equal to 0. So option C is the correct answer. Clear?